Hello everyone, my name is Swarnali and I'm going to be talking about my DA5030 Fall 2024 final project, which is Recurrence of Differentiated Thyroid Cancer, a Prediction Activity. So, starting with the overview of the data. So, this data that has been used has been collected from the UC Irvine Machine Learning Repository, and this data can be obtained from this link mentioned right over here. Now, if I want to explain in just what the data is about, basically this data talks about the whether differentiated thyroid cancer has recurred in patients or not. So there are a total of 383 patients in this data set, and each of these patients have been followed over a duration of 15 years. And they have been followed to see if the thyroid cancer, which they were diagnosed with once, has recurred or not. And they've also been recorded for a number of clinical pathological features like age, gender, smoking, radiotherapy, pathology of their thyroid cancer, the stage at which the thyroid cancer was detected. And there's a final outcome column, which is basically recurrence, and it has values of either yes or no. And all of these columns, like smoking, radiotherapy, pathology, everything is categorical in nature except for the age column. So basically, like each of these predictor columns are being used to predict whether or not the thyroid cancer in these patients is recurring over a bunch of years. So a business understanding is, so this is just a pictorial representation of what thyroid cancer is. So thyroid is a globular structure found on the trachea, and any sort of growth which is unusual or which is not benign is can be related to thyroid cancer. So, like, very simple, what was the goal? The goal was to predict whether or not the cancer has recurred over the duration of which the data has been collected. What is the basic workflow? So I built, so since this is a predictive modeling project, I built three models: logistic regression, random forest, and KNN. And the performance of each of these models was evaluated using metrics like accuracy, precision, sensitivity, and specificity. So after building these three base models, an ensemble model was built, and the performance of this ensemble model was compared to the performance of each of these like base models. And we'll be talking about that more in the later portion of this presentation. And finally, what was the outcome? So we successfully predicted whether or not the cancer recurred in these patients. Talking about data exploration, which is one of the first steps that we normally do whenever we have a data set to like this to work with. Some of the functions that I used to like gain an overview of the data set was str and summary. So I'm just going to like switch over to my code right here and show my RMD file, where initially I've begun with giving an overview of the project, just the way I talked about right now. And I talked about the objectives and the basic workflow, and of course the data acquisition steps. So I just installed all the packages, loaded them, and I also like loaded the data. So once I did str and summary, so this is, I get to know about all of the nature of the entire data set, and then I also looked at missing values. Fortunately, there are no missing values, but then we will be simulating missing values in the later steps of this analysis. The next step was to construct bar plots to look at how some of the predictor variables impacted the target. Like, for example, we can see that how gender has, like, females have more of a predisposition to, like, occurrence of reoccurrence of thyroid cancer. Then we can see that the papillary pathology of the tumor has more of a chance of getting recurred as compared to, say, like micropapillary, which has like zero, like there's no recurrence in that pathology. So this is the code for generating all of those bar plots. We also looked at class imbalance to see if there is like a class imbalance. Whatever class imbalance is there, we will be rectifying that by doing like weighted model building. uh, the next step was, yeah, we also checked the distribution of the numerical column. Since age is the only numerical column in this data set, we performed like a Shapiro test to see if the distribution is normal or not, and we found that it was not normal. We also checked for outliers. Like I said, we checked for missing values, we checked for outliers, and we also performed correlation analysis. So here there's the checking of outliers. Fortunately, again, there are no outliers here. We checked for the data distribution. And then finally, we did correlation analysis using chi-square testing. So over here, we are looking at how the all of the predictor variables are sort of interacting with each other as well as the recurring column. The next step is data transformation. So I did one hot encoding for all the categorical columns to make it suitable for the algorithms that I selected. Uh, I made it suitable such that the algorithms can read the data. I also did some feature engineering by combining the T, N, and M columns to give a combined column called severity. So basically, T, N, M is like a cancer classification metric, wherein T stands for definition of primary tumor, wherein you can T0, T1, T2, T3, T4, they all stand for different stages of the tumor. N is whether the lymph nodes have been affected or not, and M is the metastasis category. So even this data set had like different stages of T, N, and M, and I basically combined all these T, N, and M columns to give one common column, which is the severity score. And this has been done previously in such studies as well. So this is where I uh, okay, this is where I did. So this is where I did the one hot encoding, and this is where I did the PCA, and here is the T and M. But then I'll just run this code sequentially so that I don't run into errors. Yes, so I did identify some missing values by randomly taking out values and then imputing those missing values using the column means. I did one hot encoding. Yes, there you go. I calculated the principal components and I made a scree plot to show the principal components. And just over here is where we did the feature engineering. Yes. Then we also normalized the data, and we normalized the age column as well as the severity columns. These were the numerical columns. Finally, we are going to come to the models built. So, like I said, we selected logistic regression, decision tree, and KNN. Why were these models selected? Because all three are pretty suitable for classification tasks. None of these models make assumptions about the distribution of the data. These models are easy to train and they're easy to interpret. So, logistic regression, it is a binary classification system that produces a probability value between 0 and 1. I did use bagging to enhance the performance of this particular model. So over here, again, I've written a little in the RMD, I've written a little bit about what logistic regression is. And over here, we will be running the code which builds the model. We have the confusion matrix right here. I'll be talking about the confusion matrix in the next slide. We are also doing performance analysis and we're looking into the accuracy, sensitivity, specificity, and precision for this model. The next model that I selected was random forest. So, random forest or decision tree is a powerful machine learning algorithm used for both classification and regression tasks. How this works is basically it creates a number of decision trees during the training phase, and it uses these decision trees to basically like reach a conclusion and predict, especially for classification tasks. And I personally use the package random forest, which automatically uses bagging within its algorithm itself. So definitely, like, this is like one step reduced for me. So I'm just going to run the model here. Again, I've written a little bit about random forests and decision trees, and I'm going to run the code for the model building. I again have the confusion matrix. I'll be talking about this in the next slide, and the performance analysis as well. There we go. And finally, we have the KNN model, which is a supervised machine learning algorithm used for both classification and regression tasks. I did perform one hot encoding to make the data more compatible with KNN. And I'll just run the code. There we go. And we finally have a model comparison code as well. So I'll be talking about all of these. So let's look at the performance of each of these models. So as we can see for logistic regression, it has done a pretty decent job at predicting the recurred and the not recurred pretty accurately. And it has more instances of false positives as compared to false negatives with a pretty decent accuracy score as well. when we look at random forest, this is also doing a pretty good job at like talking about the record and not record. But what is uh, like what I feel is the situation here is that it has a pretty high accuracy, and there are evidences to overfitting as well, which we will see later. And when we look at KNN, it has a lot of false negatives. The accuracy is pretty decent, but then the false negatives are pretty high, which is pretty dangerous when it comes to such sort of like medical diagnosis, because false negatives are never good. False positives are still workable because we tend to go on the safety side more, but then false negatives are never preferable in medicine. When we evaluate the model in terms of metrics, this is why I said that believe that random forest has some overfitting, because the specificity is like near perfect. It's actually perfect. So and KNN has a lot of like false negatives. So I believe that logistic regression is performing the best in this situation. Finally, we built the ensemble model. So, what is ensemble model? Ensemble model is a combination of all three base models. It utilizes the strengths of the individual base models and cuts down on the individual weaknesses. So, I'm going to run the code for the ensemble model. So, first, I built a function to make this model, and then I applied this function on our test data. Here we have the confusion matrix, and then we will also like do some performance analysis, and then we'll compare the ensemble with the other three base models. So yes, I'll just go here. We can see that the accuracy is pretty good. It's almost like it's 89%, which is pretty decent, but even this is having some issues with false negatives. It is definitely like we can see some evidence of false negatives, but then I believe the logistic regression closely followed by ensemble model is probably performing the best out of all of these four models that we've built. We can also see this particular plot over here, that we have compared the accuracy, precision, sensitivity, and specificity of all the four models, and here we can make an informed decision as to which model we would like to select for its prediction accuracy. This finally brings me to the summary of this entire project. So, like I said, logistic regression and the ensemble models perform the best, especially since the random forest or the decision tree model showed some evidence of overfitting. One model cannot be said to be the most optimal one, thereby proving the no free lunch theorem. All the models have their strengths and weaknesses, and discretion, along with experience, should be used to select the most appropriate model depending on the needs of the data. So this brings me to the end of this presentation, as well as the entire project. It was a great experience working on this, and thank you for listening.